and then worked on while I was also doing a postdoc in Auckland, and then kind of forms the basis for the work, that kind of ongoing research that I'm doing here at Loughborough, which I kind of started in Loughborough last summer. But first up, some acknowledgements. So the work I'm going to talk to you about today is basically work from a paper which we published last year. So it's open access in ESPL, so please feel free to go and have a look at that. So just acknowledge my co-authors, Dimitri and Philippe, who just did the introduction, both in Rennes, Stefan, who is in Toulouse, who's done a lot of work in the Rangatik River, and also Luke, who started some of the very early work on this topic when he did a research internship in Rennes a few years ago. And also acknowledge Maxime and Claire, who helped us measure thousands of the grain size of thousands of grains here in New Zealand. Also Jean-Jacques for the experiments, Philippe for developing the model, and then Heidi for supporting me while I was working in Auckland. So there's going to be two parts to this talk. Really, the first half is looking at the Rangatik River in New Zealand, and then the second half is looking at a series of small-scale box flume experiments, looking at basically together the river New Zealand and the box flume is looking at the impact of sediment on bedrock channel geometry. So I'm going to start with a very kind of brief background section on mountain rivers. I appreciate that many of you will know this extremely well, probably better than I do, but there might be some people listening who aren't familiar with this, so I'll just give some brief background. So as I'm sure many of you know, that the river network forms the backbone of any mountain range, and therefore kind of makes sense that the action of the rivers in the bottom of these valleys is fundamentally important in controlling the size, shape, and morphology of that mountain range. One of the ways it does this is through responding to changes in tectonics or climate. So, for example, if we have a change in uplift rate or a change in the base level, we can generate nick points in the river system, which then, as they propagate upstream, they then have an impact on the hill slopes. This nice diagram from Martin Hurst's work. Downstream of the nick point, we have longer hill slopes and steeper hill slopes than upstream. So therefore, if we can understand the processes at work in the bottom of these valleys in the river channel, that kind of helps us understand the wider evolution of landscapes. And one of the common approaches that we think about bedrock river is based on this concept of stream power, which is basically the amount of energy within the river. And we often assume that erosion is proportional to the stream power. It gives us this equation: the erosion rate is equal to some erodibility constant K multiplied by the drainage area and the channel slope. One of the reasons we use this is it's relatively simple, and we can calculate these components from DEMs and from maps. We can calculate drainage area, we can calculate channel slope, and that gives us an estimate of the erosion rate. And then it also kind of follows that the two aspects of channel geometry, so the slope is inversely proportional to the drainage area. So as we increase the drainage area, the channel slope decreases. But when we increase the drainage area, the channel width increases, which is probably concepts you're familiar with observing rivers in the landscape. And this model works pretty well in many places, and it's quite popular, but because it's based on the energy available in the river, it fails to capture the complexities of some of the erosion processes at work within rivers. So just briefly, some of those things. It doesn't consider the role of sediment. We've known about the tools and cover effect for several years now. There's also, in its simplest form, doesn't really consider the impact of thresholds between different erosion regimes. Neither the impact of extreme flood events, which, while relatively rare on a human timescale, are relatively common on a geological timescale, and also fails to fully kind of capture the erosion processes at waterfalls when the slope is vertical due to the exponent, which, as I showed previously, these upstream migrations of these transient features is pretty important for understanding landscape evolution. So much of my work over the previous few years has been looking at a number of these aspects. So waterfall erosion, extreme flood events in Iceland, coupled with thresholds between different erosion regimes. But what I'm going to talk about today is this top one. So the impact of sediment on bedrock channel processes and channel geometry. So Bedrock channel width is kind of it's been shown in a number of papers. It's not a complete reference of kind of important papers on this topic. There's loads more, just picked out some key ones, but we know that bedrock channel width is kind of a function of different parameters. So incision rate's important, the type of lithology, discharge. Recent modelling work by Jens Tarowski and Ting and Lee has looked at nice work of bedload moving through bedrock channels impacting lateral erosion. And then in gravel bed rivers, sediment supply and grain size is also important. So this work that I'm going to talk about today has a relatively simple aim. As you can see in this nice drone video of the Rangatik River, sediment's pretty kind of critical to this system. We have the channel, we have different bars in the system, we have undercutting of the cliffs, which is then collapsing here. We have different vegetated small terraces within the channel. So the aim of this work is essentially trying to isolate the impact of coarse bedload on channel geometry. I'm going to do that through two examples. The first, looking at the Rangatik River here in New Zealand, and then also those small box flume experiments. So the Rangatik River, as mentioned, it is in New Zealand. Lots of geomorphologists work in New Zealand, especially on the South Island, because of how tectonically active it is. The Rangatik is in the North Island. For those of you who know New Zealand, this is a hillshade. These are the large volcanoes in the centre of the North Island. This is Ruapehu and Tongariro. The Rangatik River drains to the south coast, and it's a really kind of interesting river and really nice kind of natural laboratory for studying the impact of sediment on channel geometry. So this is a Google Earth image looking to the east. This is north off to the left, and the channel's kind of characterized by essentially it's currently an incised canyon, as you can see, coming flowing towards us here, with a reasonably large strath terrace which was abandoned in the past 11,000 years. As you can see in the top, hopefully the patterns of the former braided river flowing across the top of this terrace. In the present day, it's incised about 75 meters below this large terrace. And some work by Stéphane Bonnet recently did using OSL dating of the terraces, identified that this incision occurred in a non-linear fashion. So after about 11,000 years ago, relatively rapid incision, abandoning this T1 terrace, and then more recently there's been gradual abandonment of non-paired terraces, these post-T1 terraces at a more steady rate of about 2 millimeters per year, which matches kind of the uplift rate in the region. But the reason we're interested in this location for looking at the impact of course bedload is due to the spatial variability in the lithology. So this here's a lithological map. In yellow is the Mesozoic basement rock, which basically runs down the spine of New Zealand. Most of this is grey wacky material, which is highlighted by the speckled areas. Most of the Rangatik, the headwaters drain this grey wacky material, and for much of its length, it flows over basically mudstones and sandstones, uplifted marine deposits. And what's really interesting is a number of these tributaries which drain in from the east, the headwaters tap into this grey wacky material, which supplies basically hard pieces of gravel as bedload into the river system, which then flows through the mudstones and the sandstones, which is really quite weak, and then down to the coast. While there's tributaries over to the west, which don't drain any of this grey wacky material. Their whole catchment is within the mudstone and the sandstone. So we have this really nice spatially distinct contrast in the lithology, which therefore supplying spatially distinct sediment as bedload to the system. And we can see that qualitatively as you move around the catchment. So these photos are taken from a variety of different locations labeled with the letters. So point A, here, this is the Makahini tributary. This only drains the mudstone and the sandstone. As you can see, and it's not a great photo, I'm sorry, it's from a bridge. It's relatively narrow, it's not particularly incised, and there's no obvious sediment in the bottom of this channel. There's not much going on. And the same, we see that in photos B and C in the Hautapu tributary. Again, relatively narrow, no sediment in the bottom, though this photo here, C close to the tributary with the rangatik is a slot canyon, but it's really narrow. And again, there's not much sediment in the bottom. Meanwhile, in contrast, these photos on the right-hand side, this photo D of the Kafutau tributary is taken close to basically a lot of upstream in this area is draining the Greywacke. You can see it's massively in size from that terrace. It's about 75 meters of elevation. We have huge amounts of sediment stored in the bottom of the channel. We've got multiple active threads. We've got bars. We've got small vegetated terraces forming, vegetated bars. And we see that again in the main trunk channel of the rangatik. So this photo E is taken upstream of photo F. It's reasonably large catchment, but a large amount of that drains the Greywacke. And again, you can see that material, these white areas in the channel bed. The rangatik itself here is downstream of the confluence with the Kafutau. And again, there's lots of sediment in the bottom. It's just quite a high drone photo, but there's multiple bars on the inside and the outside of these meanders. So to basically explore this phenomenon in a little bit more detail, we basically extracted systematically the channel width over the region. So across multiple tributaries, those which drain the Greywacke and those which don't, which are indicated by these red dots. So, but at each of these red dots, the locations, we extracted the channel width from Google Earth. We calculated the upstream drainage area and also the proportion of the upstream catchment which drains Greywacke, using that as a proxy for the supply of coarse bedload. So these points here on the right, which are close to the Greywacke source, they'll have a high percentage of Greywacke. So in theory, they have a proxy for a higher bedload proportion of coarse bedload coming in, while these catchments off to the east, the Makahini, for example, has no Greywacke in it, so that would have a value of 0. These white dots indicate locations where we measured the grain size just to get an idea of the characteristics of the sediment. And then these black dots are locations of weather stations that we use to convert catchment area to a mean daily discharge to remove any kind of orographic effect. So essentially what we have here is a study area where we're able to remove impacts such as the orographic effect, large scale changes in lithology, because all of our measurements are taken from the mudstone and the sandstone. So yeah, basically we're trying to isolate here the impact of the coarse bedload. And this is what we have. So if we look at the top plot on the left hand side, we've plotted the channel width against the mean daily discharge. As you can see, if we look at all of the points together, we have an increasing relationship between width and discharge, which is what we'd expect to see. But what's interesting is we look at the coloring of the points. These white open symbols are all measurements of channel width in locations where there is no supply of coarse bedload by Greywacke. So there's no proportion of the upstream catchment that is made up of Greywacke. Meanwhile, varying shades up to black is increasing proportion of catchment draining Greywacke, so an increasing proxy of bedload. And what's really interesting here is all of the points seem to have a systematic difference between the channel widths for a given discharge, basically depending on whether the catchment drains Greywacke or not. This second plot, we show that in a little bit more detail. Here we've normalized the channel width by the square root of discharge to try and remove that increasing effect. And again, for a given discharge, we have up to an order of magnitude spread or difference between catchments which don't drain Greywacke and catchments which do have a supply of the coarse bedload. And then at the bottom here, we've binned the widths based on their proportion of catchment draining Greywacke and plotted against the normalized channel width. As you can see here at the bottom, those which don't have any are really quite narrow compared to the others, and there does seem to be, it's a bit noisy, but there is an increase in the normalized channel width with the increase in catchment draining Greywacke. So that was a really interesting observation, and we just wanted to check to see if whether the spread in this data was based on the grain size that we measured. And what we have plotted here is the distance from the greywacke source along the x-axis and then the grain size. So it's a bit of a messy plot, I'm sorry about that. But the points are the D50, and then the dashed lines are the range from D10 to D90. So across even the coarsest grains and the D50, there's no obvious trend in downstream fining across this short distance from basically the front of the mountain range to the sampling location. So this kind of pattern that we're seeing is the reason we tested this was because we were thinking that maybe the highest normalized channel widths were purely because they were close to the source of the greywacke. So the greywacke is larger, and therefore maybe it's having a bigger impact when it impacts the channel banks. But and then here decreasing because the grain size is smaller, but doesn't appear to be the case in our measurements of the grain size. But in any case, what we really kind of interesting finding here from the rangatik that there appears to be this, whether it's a threshold or just an on-off switch, effectively, of having the presence of bedload causing this channel widening compared to the catchments which don't. In order to kind of explore that process in more detail, that's where we decided to do some flume experiments, basically, which were done in the flume system that I set up and ran a couple of years ago during my postdoc there. One second. It's a relatively small flume. It's only 80 centimeters long. It's about 30 centimeters wide. And then we can control the width and the length and the slope. This is it in its smallest setting, but we can increase the width up to 0.5 meter, and it can go up to 3 meters long if we wanted to. This white material that you can see in the photo is a cohesive homogeneous silica paste with a really fine grain size. Effectively, this silica, when you mix it with water, becomes cohesive, so it behaves more like a bedrock channel rather than just using normal sand, which we'd only get an alluvial channel in the flume. We can control the amount of water coming in from the top. This is the water's flowing towards us. This is a reservoir at the top, and we also have a sediment feeder set up, which can add sand to the system. So the sand is coarse. It's coarser than the silica, 250 microns. Still relatively fine, but yeah. And we can control this sediment coming in at the top. At the bottom here, you can see the outlet. This is a door basically that we can move up and down to either at a regular pace or just move it down to simulate a drop in base level. And during the experiments, we have a terrestrial laser scanner set up. So this green light you can see here, and this allows us to collect high resolution images of the topography fairly frequently during the experiments. So we've used this flume for a number of different studies. So we've looked at the nature of the silica, so different mixes of silica, giving it different cohesions, and looking at the impact of different discharges on the retreat of nick points, having drops the base level, and we've also looked at the formation of terraces based on changing either discharge or the sediment supply coming in. Those are in a couple of other papers, but these experiments I'm going to talk about today are relatively simple. We just drop the base level once to channelize the flow, and then we just leave it with a different sediment supply for 4 hours, and we look at the nature of the channel at the end of that, well, and during that. So as I said, we have a terrestrial laser scanner set up during the experiment. This is an example of one of the point clouds. We grid that at 2 millimeter resolution to generate DEMs. And as we have laser scans every couple of minutes, we basically can put those DEMs together. We get really nice animation of how the topography is changing during the experiment. So there you saw there was an upstream migrating nick point initially where we dropped the base level to channelize the flow, and then this is an experiment where we start to change the sediment supply, and you can see the response to the channel. That's not actually what I'm going to be talking about today, but just kind of showing how this kind of high resolution images of how the topography is changing. We then couple that topographic data with a numerical model developed by Philippe Davy. Essentially, we give that model the DEM. We tell it where the input of the water is. We tell it where the output of the water is, and then the model basically flows water over the surface after calibrating things like the friction coefficient. And then that gives us kind of high resolution information, hydrological information during the course of the experiment. So this here is the flow of water colored by the water depth. So the darker blue is the darker, deeper water essentially. And from this, we can then automatically extract things from like the channel width. We can count the number of pixels which have water present and the depth of that water. We can calculate things like the shear stress based on the slope and the depth of the water. So that's the type of data that we're working with during these experiments. And what I have for you today is basically 7 different experiments. They were all run with a constant water discharge of 1.5 liters per minute. They all had the same setup in terms of the type of silica and initial conditions. So starting with a flat surface, we drop the base level by a few centimeters. That propagates the nick point up to the input, which channelizes the flow. And as it does that, the channel is free to self-form its width and self-form its slope. So you can see here that the width that you can see has not been cut by us, that's just been cut by the channel itself. And then we have 7 different experiments with different sediment fluxes from the sediment feeder. So initially, we have no sediment at all. I should say that the silica can be eroded by hydraulic shear rather than abrasion. So what we're looking at here is more of a cover effect rather than a tools effect. And then we increase the sediment flux for the different tests, each of which are all started with that initial channelization phase. All of the experiments, apart from the last one with the highest sediment flux, had the silica banks. As you can see here, the banks of the channel are the cohesive silica. They're not alluvial banks. Although where we had the highest sediment flux, the sediment supply was basically too much and buried the banks and started to behave more like an alluvial channel. So the reason we maintain that in here is just for a comparison between kind of alluvial conditions and these kind of mixed bedrock banks with, in some cases, the bed completely covered by the input sand. So what we have here is the extracted channel width and the slope, and then the calculated width-depth ratio based on the model output under the different sediment supplies for basically all of the DMs that we extracted after that initial channelization phase when the nick point's moving up. So after that, the channel is basically just settling down and adjusting to the constant conditions of the sediment supply and the water discharge. And what you can see here is effectively an increase in the channel width, an increase in the channel slope, and an increase in the width-depth ratio as you increase the sediment supply. Admittedly, there's quite a lot of overlap between the different experiments, but hopefully you can see that trend. What's also interesting here is the relatively narrow ranges of width and slope and width-depth ratio we have for the example where we have no sediment supply. Relatively constant once it's formed its width and its slope, and then increasing ranges as we increase the sediment supply. So what we have for you here now on the left is the examples of the DEMs at the end of each of these experiments, at the end of the 4 hours, so the channels had a chance to adjust to those conditions. So we have an aerial view of the DEM with the water depth map plotted over the top, and then on the right hand side we have a channel cross section in black extracted from the channel midpoint, and then in red is the shear stress across this cross section plotted as a normalized shear stress between the shear stress at each point divided by the maximum shear stress in that cross section. So as you can see, as we move down the page and we increase the sediment supply, we appear to get an increase in the channel width you can see in both visually in the cross sections and the DEMs, and also what looks like a variability in the distribution of shear stress across the channel. And then what we have plotted on the right here is the average channel width and the average channel slope for these conditions at the end of the experiment. So the arrow bars are the average width for all of the points in the central part of the channel. So we ignore the bit at the bottom and a bit at the top to remove any impacts of the inlet or the outlet. So we have the average channel width, and then we have multiple measurements of channel slope as well across the channel. And as you can see here, so the square points of these experiments you can see are on the left-hand side. The white square is the example where we have no sediment supply, and the increasing in grey goes up to black where we have the highest sediment supply. Now the star is there is to remind you that that 20 grams per litre is under alluvial conditions, which you can see in the DEM. The water there is flowing right to the edge of the box, and it's basically all alluvial, whereas as the others you can see the bedrock banks in the DEMs. And what I've also plotted here on the right hand side in the circles is a comparison data set from some experiments I did looking at waterfall migration, which all had no input sediment supply but was performed at different water discharges. So that's what these numbers are. These numbers indicate the constant water discharge for these experiments. And for those experiments, as you can see, as you increase the water discharge, you increase the channel width, and you also decrease the channel slope, which is what we expect to see in natural channels. What's interesting from this plot is the wide range of possible width slope configurations that we get with just at a single water discharge. So all these square points are at a constant water discharge, just changing the sediment supply, and we get this big range in width slope space, which I think is quite interesting and important for thinking about how we use channel geometry for reconstructing paleo conditions, for example. So we then looked at the shear stress in more detail during these experiments using that water model, that numerical model output for the water depth. And it's quite interesting here that we don't seem to see, so plotted in red is the critical shear stress for transporting the material, and then the box plots show the medium and then the range of shear stress values based on the water depth and the hydraulic slope in the experiments. And interestingly here, we don't seem to see an obvious increase in the shear stress, the mean shear stress of all the pixels within the channel. So the channel seems to be adjusting its width to maintain a relatively constant shear stress, which is about 3 to 4 times higher than the critical shear stress required for sediment transport. So looking at that in more detail, what we have at the bottom here is we calculate the excess shear stress for each of the pixels. So that's the shear stress measured minus the critical shear stress. And then across the cross section, we then add up the total of those excess shear stress values. So therefore kind of makes sense that as the channels get wider, there's more pixels which therefore have a higher total excess shear stress across the whole width of the channel, which I guess makes sense for requiring to transport those higher sediment loads that are coming in. Interestingly, it seems to be relatively constant at a low discharge between 0 and 5 grams per litre, and then we start to see an increase above 5 grams per litre. And this also corresponds with observations from the images. It's above 5 grams per litre that we start to see the bed completely covered by sediment, and below 5 grams per litre of sediment coming in, that's where we still have quite a lot of patches of the silica bed, suggesting that maybe some sort of transition between supply limited and transport limited channels occurring at this sediment flux, but need to kind of drill into that in a little bit more detail to be able to be sure about what that transition might be. So we seem to have this relatively constant mean shear stress across the cross sections, and then this increasing excess shear stress when we increase the sediment supply. But while we have a relatively constant mean shear stress, the distribution of the shear stress within the channel is not constant, which we explore here in a little bit more detail. So this is a map of the normalized shear stress for one of the experiments where we have no input sediment flux. So we have 20 cross sections. Sorry, the x-axis is at the bottom of the page. It will be revealed shortly. We have 20 cross sections extracted from this kind of study area, well, the study reach. And then for each of the pixels, we calculate the maximum shear stress for the entire cross section, and then the normalized shear stress for each pixel. So that's the shear stress divided by the maximum shear stress. So values that are black are all close to that maximum shear stress, whereas white values are much lower. So as you can see here, everything seems relatively uniform, relatively constant around that maximum shear stress. And you can see that in the example DEM. It seems relatively uniform, almost like canal-like conditions, and we have no input sediment supply. What we have here in the middle is just another example of a DEM. So 2 minutes before this first one on the left-hand side, again, we have relatively constant shear stresses within the channel. And that's shown on the right-hand side in a PDF where we have 5, with data taken from five of these DEMs. This is the normalized shear stress across the bottom, and you can see most of the points seem to be around 0.7, 0.8. And for reference, these dashed lines are the critical shear stress. So we have a clustering of most of the points around 0.7 to 0.8 normalized shear stress. This second line then shows the same data sets, but for the experiment with 2.5 grams per litre. Again, there seems to be quite a lot of areas of black close to that peak shear stress, but there's a bit of a flattening off of the PDF as things move down to maybe 0.5, 0.6. So it seems to be a slightly more varied distribution of shear stress, but still relatively uniform, especially compared to higher shear stresses. So these are the two highest examples, experiments with the highest sediment flux. So if we look at the shape of the PDFs on the right hand side, we can see that the peaks are closer to 0.1, 0.2. So most of the pixels that have water in them, the shear stress is much lower than that peak shear stress, and you can see that in the maps of these maps on the left hand side. So there's areas where the shear stress is, well, the areas are black, suggesting that's where the peak shear stress is. But then there's large areas of the channel where the normalized shear stress is really quite low, suggesting that the sediment flux is kind of focused in these narrower areas. And what's also interesting here between these two plots is that these two plots are only 2 minutes apart, but there's quite a big shift in the distribution of the shear stress. So the channels here are quite dynamic and shifting around. So this is all with a constant water discharge, just changing the sediment flux seems to kind of control the morphodynamic behavior of sediment transport within the channel as well as changing the channel geometry. So just as an attempt to try and link all these different data sets together, so link the experimental data set to the New Zealand example, we've normalized the width and normalized the discharge and able to compare it to previously published examples of channel geometry, which taken the data from Francois Métivier's paper in 2017 in eSurf, which is a really nice compilation of channels looking at the difference between single thread and braided. So that these lines here are the values that we'd expect from threshold theory based on black, and then the dashed lines are basically a range of values for the threshold theory based on different constants. And then the red points are the points from the Métivier compilation based on the single thread values, and the orange are then the compilation based on braided channels, suggesting that as you have a higher sediment supply, you move away from the threshold theory and you get a transition in the morphodynamic behavior. If we then look at the symbols that we have on the plot. This is from the experimental data. So these crosses are the data set I talked about before, the waterfall experiments, all with no sediment supply, but a different range of discharges. These plot relatively closely to, well, they basically plot on the threshold theory line. And then these symbols indicate the experiments with the different sediment supplies. They're plotted in two places because the normalization of discharge based on the D50 was whether they were predominantly flowing over the silica or over the sand, which is why we have two data sets. But if we look at the position of these points relative to threshold theory, as we increase the sediment supply, we plot further away from the threshold line, and you can also see that in the data set from the rangatik, which are the coloured squares. Again, these are covered by the proportion of the catchment draining grey-wacky, so these lighter points, which plot closer to the threshold theory, are the experiments, the locations where there's a lower proportion of the catchment, a lower proxy of coarse bedload, while these points with the darker grey are the ones with the higher proportion draining grey-wacky. So that's kind of interesting that the bedrock and the gravel rivers, both from the experiments and from the rangatik, appear to follow a similar behaviour to the compilation of the alluvial channels based on the Mativier data set. So that's kind of an interesting way, hopefully, of linking these things together. So kind of coming towards the end of the talk. So just to summarize things, there's a systematically larger channel widths in the rangatik catchment driven by this availability of the coarse bedload, depending on whether they drain grey-wacky or not. And this appears to be potentially an impact of the cover effect driving more lateral erosion by sediment impacts. Based on the experiments, we seem, and also the New Zealand data set, we appear to have a range of possible channel geometry configurations for a given discharge. So remember that plot of width against slope. This, I think, the potentially important consideration for thinking about how we use channel geometry for other reasons. We can't assume that there's a linear or whatever relationship, a simple relationship with discharge. And also that we potentially have, we have increasingly complex distribution of shear stress within channels and changing channel morphodynamics with the higher sediment supply, which is relatively well known in alluvial channels, but also has been identified in these bedrock and mixed bedrock gravel channels. Yeah, so just finally, I know this is a little bit cheeky, but here at Loughborough, we're currently recruiting for our taught masters courses, and there is one in particular that might be interesting to people if they're looking for a master's program, this environmental monitoring, research and management. So if anyone's interested in that, there's a web link, and feel free to get in touch. But I will leave the talk there and hopefully answer any questions that you might have if I can find the chat box.
Thank you very much, Ed, for your very nice talk. So the chat is open for questions, so don't hesitate to use it. Once again, if you want to directly ask your question with a mic, you can just raise your hand and we will give you access to the mic. So right now there is no question. So maybe Ed, I have one. There is one. Sorry, I will ask mine later. So it's a question by Adam Bug. Working in flumes can present some issues when planning. Were there any issues that you came across when in the planning process?
Well, I guess that question relates to the experimental design of the flume experiments that we did. So these experiments that I talked about today were at the end of a sequence of experiments that I'd done looking at a variety of different things. So I talked about the waterfall experiments and the terrace formation experiments. I guess in terms of the setup, it was reasonably well defined in terms of we knew that we could control the sediment supply coming in and can control the water discharge. So yeah, it was relatively easy to plan. We set out knowing that we wanted to test a range of different sediment supplies and then monitor how the channels evolved. Hopefully that answers the question.
Yeah, thank you, Ed. So I will be asking the question together also with Steffi and Steffi Tofelde, sorry, and Rebecca Harris. I can see that Alex Whitaker wants to ask a question. So Alex, you should be able to unmute yourself and to start your video as well if you wish to.
Yeah, cool. I really enjoyed your talk, Ed. I wanted to know a bit more about what you thought about the mechanisms of what was going on that was driving this widening. Is it really the case that the excess sediment is meaning that you got greater shear stress on the banks, or are we essentially looking at a kinematic process? In other words, the channels are more dynamic and are migrating more rapidly when the sediment supply is high.
In the experimental part?
Yeah, in the experimental work.
Yeah.
I mean,
yeah, I think so.
perhaps you might want to link that to the New Zealand fields example as well. But that was the part that I was really just thinking about.
Yeah, so I think what's interesting is that the channels in the experiments were adapting their width in order to maintain their mean shear stress above 3 to 4 times above the critical shear stress. But in order to then transport the sediment, they needed to accommodate that excess sediment by being wider. I think what's interesting in the experiments is that there's no tools effect in a way. So it's the sediment is protecting the bed. So it's what I didn't talk about. Well, I guess I did in the morphodynamics part, is that the channels become more sinuous and more active and moving around within the channel banks, so driving that focus of energy on the banks, which is driving that widening process. And in terms of linking that to the New Zealand example, yeah, I think again we're seeing the cover effect of the excess sediment protecting the bed and then driving the lateral erosion. Whether that's always been the case, I think because there was that period of increased incision when those terraces were initially being abandoned, when there was rapid vertical incision, and it's now settled down more towards the background uplift rate, and we're seeing kind of smaller terraces lower down on kind of the outside of meander bends. Whether that process is what we're seeing as well, directing the impacts against the bank. I think that's what we're seeing, rather than necessarily a higher shear stress in individual locations.
Sure. All right. Cool.
Thanks, Alex.
Thanks,
Ed.
So we have another question. Maybe Steffi, you want to go on?
Yes, although I actually would, before I read out Jesse Zanderveen's question, I would ask a question myself, because it's kind of a follow-up to Alex's question. So in New Zealand, you were particularly looking at bedload transported sediment. And in your experiment, do you have any idea about the fraction of sediment that is, or how the sediment is transported, if the majority is transported just in suspension, or do you have actually bedload transport? Okay. I understand it's totally hard to see this in the experiment, but maybe you have an idea?
Yeah, so we definitely have bedload transport in the experiment. So it's quite hard to see. Well, you can't see it in those animations, but you're able to see visually while you're watching the experiments the development of sheets along the bottom, which are clearly showing sand migrating slowly along the bottom of the channel. So a migrating front with the recirculation of material. So it is this kind of bedload sheet moving down through the experiment. Yeah, and I think in New Zealand, again, it's mostly bedload with the grey wacky material, mostly because the mudstone and the sandstone. So you can see in the background of that picture in the slides, that's the mudstone during a rainstorm basically, and it gets really wet and really quite soft. So when that breaks down and gets into the river, that basically is transported out that's more in suspension. So the bedload material will likely be that grey wacky material coming down. And then in the experiments, yeah, there's definitely bedload transport, as well as, again, once the silica gets eroded, while some gets incorporated into that bedload material, most of it is just transported straight out in suspension.
Okay, thanks a lot. Then I'll just continue, if that's okay, to read out the next question from the chat. It's a question by Jesse Zonderveen. He thanks you for the talk. And could you elaborate on your ideas around thresholds? How could your results inform the approach to numerical modeling of alluvial landscapes like rivers and river terraces?
Yes, that's a nice question. Something that we initially kind of set out thinking, well, one of my hypotheses, I guess, I wanted to test with the New Zealand data was whether there was a threshold in the proportion of the catchment draining greywacke which would start this widening process. And what we actually found if you remember back to that channel width plot, is the threshold seemed to be whether the catchment drained greywacke or it didn't drain greywacke. So where there's no greywacke, the channels were narrow, and then when it did, they were substantially wider with no obvious threshold in the amount of bedload. In terms of how to incorporate that into numerical modeling of alluvial landscapes, I guess that's a tricky one when it's an on-off switch. I guess you could incorporate that into, I guess, different processes dominating in the model, and whether this bedload dominate might be important. Yeah.
Thank you, Ed. So we have another question. Rebecca, do you want to go on?
Yep, sure. So this is from Chris Thomas. He says, "Hi Ed, thanks for a great talk. Would you expect to see tooling effects at lower sediment supplies? In your experiments, there seems to be a threshold at about 5 GL sediment supply from what you said. As sediment supply increases towards some value below 5 grams per liter, would you expect to see some tooling effects on the riverbed, deepening rather than widening of the channel before the sediment started to protect the bed?" You got that?
Yeah, so I think the threshold that we see at 5 grams per liter, in terms of the observations, that's where we start to see the bed being fully covered by the sand coming in, and whereas below that we have some sediment stored in the channel, so the bedload's migrating, but there's still areas of exposed bedrock material, well, exposed silica material. So I think whether that is a shift in the transition of the experimental channel from supply limited, where it can transport all of that material, or being transport limited, where effectively the supply coming in is too great for the supply channel, and that's where we see this shift in the excess shear stress. In terms of tooling in the experiments, I think we're always unlikely to see that just on the nature of the silica. So we're able to use the silica to explore these processes because we can scale down basically the spatial and temporal action, but we limit having the tools effect just because there is no abrasion. It erodes just by the hydraulic shear of the water flow. So I think well, yes, that would be really interesting to look at. I'm not sure it's possible in these experiments.
Thank you, Ed. So Jesse, relatively to the previous question, he said he'd like to chat a bit more about threshold and shroom at some point. So it's more an invitation.
Yeah, well, Jesse, please feel free to get in touch anytime, and we can set up a chat, email or something.
And we have a question by Linda Kirstein. Lovely talk. A quick question. What caused the incision at 11 Ka?
So I think the general incision of the area, I think, is a climate signal. So a change in the sediment supply driven by a climate signal. But I think the paper by Stefan Bonnet will go into that. So Linda, I can email that to you, and we can talk about it. I'm pretty sure that they're a sequence of climate-driven terraces, because above that terrace which abandoned 11,000 years ago, there's a sequence of our other terraces which go back much older. So yeah, I think it's in general it's a climate-driven sequence of terraces.
Okay, thanks, Ed. And the next question already came in. It's from Jean-Louis Grimaud. He also thanks you for the nice talk. And he's wondering how different the system is from braided rivers. So I think that refers to your experiments. And have you tried to replicate your experiments without the walls to compare width and slopes of the system?
Yeah, so I guess the short answer is we haven't tried experiments with a channel which is wider, although that is possible based on the setup. But we have an idea of how they respond based on that example with the highest sediment supply, when we basically started to build an alluvial fan into the system. So we have a very high sediment supply which buried the bedrock banks, and then yeah, so it does start to behave like a braided condition with, well, yeah, with multiple channels moving around within the box, but it is limited by the width of the box. So whether that would be natural is yeah, it's limited by the shape of the box, but it could be something to test and would be nice to look at. Yeah.
And maybe a quick follow-up question to this, actually.
Yeah.
Because I guess you also have done experiments with different discharge values, right? So when you start to change discharge, you will eventually change the slope. And then how does this eventually impact the changes in width?
Yes, so we haven't done any experiments with this setup under different discharges. So we have the waterfall experiments which were at different discharges but had no sediment supply, and I've done some experiments which is on my list to work up next, is basically repeating those waterfall experiments where we have a sediment supply coming in. The main aim of those was to look at whether the sediment has an impact on the morphology of the nick points as they migrate, rather than I guess looking at the transient response rather than just the steady conditions. I think, yeah, if you add in the transient aspect as well of adjusting to a new base level or a constant incision rate, that would be interesting to see how the width varies there as well.
So we have a follow-up question by Linda Kirstein. So she wondered if there is an increase in proportion of greywacke exposed at surface at that time. I think she refers to this 11 Ka incision.
Yeah, I'm not sure about that, actually. It'd be something that I'd need to look into in more detail. So something I didn't mention when I was talking about the greywacke is there is also a small supply of sediment from the abandoned terraces themselves. So they are strath bedrock terraces, but they are capped by a veneer of sediment. But yeah, in terms of driving the terrace incision, I'm not sure if, yeah, the sediment supply coming from the upstream part. So most of the terrace material is greywacke as well. So yeah, changing that sediment supply potentially by a climate signal or a lithological response could be doing that. I'm not entirely sure. I can look into it and get back to you, Linda.
Thanks very much, Ed. So if there is any other question, it's high time to ask it. Otherwise, I think we will closely end this talk. No more question? Okay, so thanks a lot, Ed. Oh, no, there is one. We have one question. So a question by John Kemper. I had great talk. Do you have a sense for how the relative hardness of the greywacke sediments versus the marine lithologies affects these relationships? Would you expect a strong relationship if the lithology was slightly different? For instance, the marine was a bit more resistant.
Yeah, I think it's a really good question. And I think the observations that we see here with the difference in the widths driven by the greywacke is so obvious in the measurements because of the difference in the strength of lithology. I think if the two lithologies were much more similar, I think that difference would be much less obvious. And in some ways, that's why it's a really nice place to look at, because that difference is so strong. So we see the impact of the presence of the bedload so much, and probably why we may not see it in other locations quite so well. But that could be an interesting thing if there are other locations where this kind of spatial pattern in the lithology is present, and the relative difference in the hardness would be interesting to look at. But I think it's so obvious here because the marine sediments are so weak. Great, thanks, John.
I say excellent. Okay, I say the same. Excellent, Ed. Thanks a lot for your very nice talk and for this good series of questions and answers. So I remind to everyone that we will have a next talk next Thursday by Alison Pfeiffer, and you can check the program on the Landscape Live website. So have a good day and see you soon.
Thanks, everybody. Stop sharing.